Okay, so we are doing the last section of the chapter, which means you'll be looking at a test at the end of the week. This is the hardest section, in my opinion, that you will encounter probably all of AP Calculus. So please make sure you pay attention, make sure you use your resources, make sure you read your textbook, make sure you use the QR codes and the homework to help you. You may look up additional YouTube videos or other resources, but related rates are really important, and the AP test loves them. But they're difficult because they're highly involved. There's a lot of steps and a lot of reading and a lot of figuring out. They always go with word problems, essentially. Okay, so ignore the wonky shape of this word problem, but the problem actually starts here. Okay, so for example, the example is when water is drained, and this is more of a definition and conversation about related rates. But when water is drained from a conical tank, this is our figure, the volume, the radius, and the height and the water level are all functions as a result of time. Okay, so as time goes on, the water level goes down. As time goes on, the volume goes down. As time goes on, the radius is going to shrink because water is going from way up here to way down here. Okay? Knowing that those variables are related in the equation is one of the reasons we call it related rates. But you have to figure out what equation relates all those variables together. So they gave us a volume for a cone, and volume is pi thirds r squared h is relating volume, radius, and height all together in the equation. If we were to differentiate this implicitly, we would be able to relate all the rates together with respect to time. So when we do these derivatives, they're all going to be with respect to time. So how we were doing derivatives, dy over dx, that's with respect to x. All of our derivatives are going to be with respect to time, so it's going to be over dt. So if we're actually to look at this, so let's just take a practice of implicitly deriving things. The derivative of v is 1. I'm going to write it just for the sake that we have it. And dv over dt. Okay, just like when we derived y, we did dy over dx, and the derivative of x was dx over dx. We didn't write it. These will have it always because you're not going to be deriving time. Pi thirds is just a number, so I'm going to leave it with the r. And if you notice, this is a product of two things, pi thirds r squared and h. So if we do 1, we'll do pi thirds r squared as our first thing. So 1 d2, derivative of h is 1, dh over dt, plus 2 d1, and that'll be 2 times pi thirds r to the first power dr over dt. And we're not going to simplify anything of that because we're not having an operation to use it for, a reason to use it for, but that's what it means to implicitly derive it so that you get related rates. So we now see how the rate that the volume is changing with respect to time is related to how the height is changing with respect to time, which is how the radius is changing with respect to time. They're all related together. So that's where related rate gets its name. So if you're asked to find a rate, make sure you're finding something over dt, because if you think of a rate as a slope, you have to have a change in something over a change in something, and our bottom denominator is always change in time. All right, so let's try this example. So we have the variables x and y, both differentiable functions of t as they are, and they're related by this given equation, y equals x squared plus 3. We're going to find the related rate, dy over dt, when x is specifically 1, given that dx over dt is equal to 2. Okay, so what we'll do is we'll first derive our function. So dy over dt, again, it says with respect to time. So we will not have a dy over dx, we'll have dy over dt, is equal to 2x dx over dt, and then the derivative of 3 is just 0. So we have this. And so paying attention to what we have, I know that x equals 1. Okay, so I can plug in 1 for x. And I know that dx over dt is 2 at that same instant. They have to be matching instants. You can't have like a t is 2 and a rate is something else and be plugging them in. It's got to be the same instance. So when x is 1, dx over dt is 2. So I'll plug in 1 for x, and I'll plug in dx over dt, which is 2, so that my slope, dy over dt, is equal to 4. Okay. So that'll be a kind of change in a habit that you're going to have to put when you derive x. You will have to put dx over dt. I often will name my variables according to what we're talking about. All right, so we have a word problem. A pebble is dropped in a calm pond, causing ripples. There's your example of your ripples. It is talking about the radius changing. So as the ripples continue, they get longer and longer and longer, or the radius gets bigger and bigger and bigger. And the outer ripple is increasing at a constant rate. Okay, so there's a pattern to how it's increasing of 1 foot per second. When the radius is 4 foot, at what rate is the total area of A of the disturbed water changing? So we're talking about an equation. It mentions at what rate is the total area of this circle. So the equation we're going to relate is area of a circle. So area of a circle is A equals pi r squared. Okay, we are given that the rate of the radius is increasing. Okay, so we will have negative rates, so pay attention to increasing, decreasing, is increasing at a constant rate of 1 foot per second. So my given rate is the change in radius. So I'm going to call it dr over dt. So this r is changing with respect to time. And dr over dt is 1 foot per second. Get in habits of putting your units, because these answers have units as part of them. All right, and then we are supposed to find, it says, what is the total area changing? What is the rate of the total area? So we're asked to find dA over dt. So we want to know how quickly the area is changing with respect to time. Okay, so always pay attention to the information given. All right, and I always like to put when it happens. We're finding d over dt when r equals 4. Okay, so that happens later on. You have to do all the implicit derivatives before you plug in a lot of your values. All right, so we are going to now derive our function. So looking here, dA over dt, the derivative of a is just 1 dA over dt, is equal to 2 pi r dr over dt, because when I derive r, I'll put dr over dt. Now, that might look familiar. The derivative area is circumference. 2 pi r is circumference. So that's not a coincidence. That's how some of those formulas are connected. So we have this. And then once I have my implicitly derived function, I can now plug in the information I know. So I don't know d over dt because that's what I want to know. 2 is 2, pi is pi, r at my specific instance is 4. And that rate at that specific instance, because it's a constant rate, so at every instant, it's 1. So sometimes there'll be specific situations where the rate is only at a certain point, but it's 1 constantly. And then we can just simplify it. 2 times 4 times 1 is 8, so we have 8 pi. Okay. And our unit will be its derivative of area. So area is, we're doing feet. Area would be squared per second. Okay. So we have that as our change in area. So if you were to answer this or answer it as a sentence, you'd say the rate of the area is changing or increasing by 8 pi feet squared per second. Okay. All right, so here's some just examples of how you would identify parts of it. So we have the velocity of a car after traveling 1 hour is 50 miles per hour. If x is your distance traveled, then your dx over dt, that rate of your distance traveled, is 50 miles per hour when t equals 1, because it says for 1 hour. So these are just examples you might refer back to if you're trying to figure out how to set up equations or what information is actually given. Some of these are helping. Water is being pumped into a swimming pool at a rate of 2 cubic meters per hour. So V is our volume, and the change in our volume with respect to time, so that rate as the volume is changing, is 10 cubic meters per hour. And you can kind of see that as it is. A revolving gear has a rate of 25 revolutions. So they'll use theta for angle of revolution per minute. And so we're doing d theta over dt. It's how quickly it's revolving. The angle is changing with respect to time. And they told us 25, and it's per 1 revolution, they put it in radians. Okay, 1 radians is 2 pi, like all the way around in a circle. And the last one to kind of help us pay attention to how things are worded, and we'll do a lot of examples that we actually have to figure out. A population of bacteria is increasing, so again, a positive rate of 2,000 per hour, And you can see where they just picked a variable. You don't always have to pick x, but you can. Number of population, dx over dt is a change in x with respect to time, or the rate as which x is changing with respect to time, is equal to 2,000 bacteria per hour. Okay, so air is being pumped into a spherical balloon. That shape potentially could tie into an equation we might use at a rate of 4.5 cubic feet per minute. Find the rate of change for the radius when the radius is 1 foot. So let's look at an equation. I kind of make a habit of writing down information here. So we'll do the equation. And the equation, we need to relate cubic feet. So that would be volume to radius. So that would just be the volume of a sphere. So volume of a sphere is 4/3 pi r cubed. If you don't know a lot of your formulas, if you go, it's either like the first page in your textbook or one of the last pages of your textbook. It's the last page in your textbook, like actually the hardback. It has volume and area of certain figures. That might be helpful for some of the problems if they don't give you the equation. All right, so then I want to do what I'm given. So information I am given. And we are given that the volume is changing, the air being pumped in, but I know it's volume because, again, the cubic feet per minute. So we know that dV over dt is 4.5 cubic feet per minute. Okay, we have that. We are supposed to find, so we're basically listing our knows and our want to knows. We're going to find the rate of change of the radius. So dr over dt. So that means the equation has to have these letters that we're using. Okay, so I'm not using x and y's. I'm using the formula as we know it. And we're wanting to find dr over dt when r equals 1. Okay, so that's what we have. So I need to then take my equation and derive it. So the derivative of v is 1, but I have to put dv over dt every time I do the derivative. And then, erase that. I need to derive this, and this looks weird, but if you keep in mind 4/3 is a number, pi is a number, so we're really just deriving the r cubed. So I'm going to have 3 times my 4/3 pi, now r squared. And we can simplify that, or you can simplify it as you go. And then since I derived r, I have to do dr over dt. Okay, let's simplify that just a little bit because I have a 3 over a 3, so I have 4 pi r squared, dr over dt. Okay, so that I have that. Now we're going to plug in the information we know. We know that dV over dt is 4.5. 4 is 4, pi is pi, and we're doing a specific instance when r is 1, dr over dt. So if you notice, we are only missing one thing. We're going to do a little more work to solve it. So I need to divide everything away from the dr over dt. So you're just going to solve like you would an algebraic expression, but we are solving for dr over dt. Okay, so I will divide by 4 pi times 1 squared, which is just 4 pi. So I'm going to divide both sides by 4 pi. And so plug that in a calculator. You could leave it like that, but fraction of decimal is not recommended. You could multiply top and bottom by 2 so that you have 9 over 8 pi. That would be okay. But we can plug it in our calculator and get an approximation because your AP test, again, they want it to 5 decimal places, so get in good habits. So this is acceptable. And you could also have 0.3581. Okay, by the time you do the rounding, your 5 decimal places will end up like that because it's 3.358098. So it's going to round up and then round up again. All right, and then your units, if you're doing radius, it's feet per minute. Keep in mind, like radius is a unit, or it's a one-dimensional measurement. So your feet or your inches is just not squared. If you're doing area, it'll be squared. If you're doing volume of some sorts, it'll be cubed. Okay. An airplane is flying on a flight path that will take it directly over a radar tracking station, and shown in the figure. And the distance s is decreasing, so we'll have a negative rate. So that's important information. At a rate of 400 miles per hour, when s is 10 miles, what is the speed of the plane, which means how fast is it going, how the distance is changing is speed, okay? But speed is always positive, so just keep that in mind. So if it's asking what the velocity is, we potentially have a negative velocity, but your speed will be positive. All right. If you think of Despicable Me and vector, it has both magnitude and direction. Velocity is a vector, so it has both magnitude and direction, amount and direction. Okay. So we need to be looking at how we're going to use this information. So if you look at this, it is a right triangle. Okay. We know a lot about right triangles. We know that if I have a right triangle, the sum of its shorter sides squared each and added is equal to the hypotenuse squared. So that would be an equation that would connect my distance, x, my s, which is the distance from the plane to the camera itself or the satellite station. And then I have the actual height of the airplane, which is 6. So we can actually use an equation from a long time ago in geometry, which is 6 squared plus x squared equals s squared. Okay, so that would be our Pythagorean theorem. We are given that the distance s is decreasing at a rate of 400 miles an hour. So that would be ds over dt. That rate of that distance is decreasing 400 miles per hour. So make sure that's negative. When s equals 10, and that's important information too. We are asked to find the speed of the plane. Okay, the speed of the plane would be dx over dt. Okay, that's what they're asking for. All right, so we have our equation. I'm going to kind of copy it down here so I can work on it. So I have 6 squared plus x squared equals s squared. You can square your 6 if you want to, but we're getting ready to derive it, so the derivative of a constant is 0. So 6 squared is 36, but the derivative of 36 is 0. But the derivative of x squared is 2x dx over dt. Okay. And the derivative of s squared is 2s ds over dt. Okay. You can simplify it a little bit. If you see there's a 2 on each side, you can divide both sides by 2 and cancel it out so that you have x dx over dt equals s ds over dt. And we can plug in the information we know. We know that x is a mystery, so we'll keep x as x. And we're trying to find dx over dt. And we know that s is 10 at the specific instance they asked me. And we know that our ds over t is negative 400. So the problem with this is I can't solve for dx over t because I don't know what x is. But I do, because they told me at the specific instance that x is 10. And if you notice with that Pythagorean theorem, I can actually solve for s. So on the side, I'm going to figure out what x is so I can plug it in. So I will do 6 squared plus 10 squared. And you have to do that. You can do it earlier, but you can't use that function to derive. You have to use the function with the variables to derive it. And then you can use these to plug in to your information, which is why I do it after, so I don't accidentally derive this function because I won't get the right answer from this one I'm writing now. So I'll have 36 plus 100 equals s squared. So I will have 136 equals s squared. Oh, if you guys were here, you would have caught my mistake. Missing you guys this way, by the way, as I erase. I hope your remote learning is successful. All right, so it is this. And I labeled this wrong. So this is 10, and that is x. All right, there we go. That's much better. So I have 36 plus x squared equals 100, and subtract 36 so that x squared is equal to 64. So x is equal to 8, and I can actually go plug that in. So 8 dx over dt is equal to negative 4,000 if I go ahead and multiply by that 10. And then I can divide both sides by 8 so that I get dx over dt is equal to negative 500 miles per hour. But since we are asked for speed specifically, the speed is equal to 500 miles per hour. Okay. So wording is important on some of that. All right, we're going to find the rate of change now of an angle of elevation. Anytime you see angle in a triangle, odds are trigonometry is going to be involved in one capacity or another. So that stuff doesn't go away. And so we are finding the rate of change of an angle of elevation of the camera shown in the picture at 10 seconds after liftoff. If you notice, the camera is at ground level. Okay. They have given us a position function S, which is 50t squared, where S is measured in feet and T is measured in seconds. And the camera is 2,000 feet from the launch pad. So if you notice, they drew our picture and they drew us a right triangle. And they actually even told us what trig function to use. So they cut out some of the stuff. They didn't have to do that. That could be something we would sketch and we would have to come up with. But they told us the equation. And I know that's the equation we need to use because we are asked to find the rate of change in angle of elevation, which is theta. And the information we have is in reference to S, which is the position function of the rocket or spaceship. All right, so the equation we're going to use is tangent theta is equal to S over 2,000. We are also given that the position is 50 t squared. We are supposed to find d theta over dt when S is equal to, or not S is equal to 10, when T is equal to 10. It says 10 seconds after takeoff. Okay. All right, so this is what we have. So I need my related rates in order to do this. I need to find my d theta dt. So we're going to derive this function, our equation, so that we can get it. So the derivative of tangent is secant squared. So the derivative of tangent theta is secant squared theta, d theta dt. Makes it a little more writing when they don't use a regular function or regular variable for us. And then we would need to derive this. Don't make S over 2,000 complicated. That's the same as 1 over 2,000 times S. So the derivative of S is just 1, and 1 times 1 over 2,000 is 1 over 2,000, ds over dt. So we have this equation here. So if we go to plug in stuff, the only thing that we're going to be able to plug in is, well, nothing. We don't have anything that we can plug in. We don't have a theta. We don't have a d theta dt. We don't have a ds over dt. So we're going to have to find more information. One thing we can do is we can easily calculate ds over dt to plug it in. So if I use this, ds over dt is equal to, multiply the 2 in the front, and we'll have 100 t dt over, hold on, my handwriting's terrible. 100 t, and then it would be dt over dt, but when we plug that in, you don't have to write the dt over dt. That's kind of like when we do x without a related rate problem. All right, so I'm going to rewrite this whole thing so that I have secant squared theta d theta over dt is equal to 1 over 2,000. But in place of ds over dt, I'm now plugging in this times 100 t, and again, that dt over dt would simplify to 1. So now that problem's really not that bad. Let's simplify a little bit more. So I have secant theta squared theta d theta over dt. That d theta over dt, by the way, is outside of that trig function, not inside of it. And I can simplify this a little bit to be 1 over 200 t, or you could do t over 200. That's kind of up to you. And so then from there, we've got to figure out a theta so that we can plug it into, or how to get theta by itself. Okay, and that's going to be the hard part, is that we need to do that. But if you notice, this function, it is a right triangle. We know a lot about right triangles. We can use Pythagorean theorem to find certain things, and that might be the direction that we need to go so that we can do this. Okay, so let's simplify it a little bit more, and let's get the d theta over dt by itself. I know there's still several variables, but it helps if we have everything on one side. So I'm going to divide both sides by secant squared theta. Looks like a Q. Something to remember is that this is the equivalent of multiplying by 1 over secant squared theta, which is cosine squared theta. And so when I rewrite this, I have d theta over dt is equal to cosine squared theta t, and I'm going to go ahead and put that 200. So I'm just multiplying all my fractions together. So just keep in mind that 1 over secant squared theta is the same thing as just cosine squared theta. So we can write it like that. And we know that cosine is adjacent over hypotenuse. And if you notice, I have my adjacent side, okay, here. And my hypotenuse, I can actually calculate using the Pythagorean theorem. Okay, so if we, I don't know, we'll just call it h for hypotenuse, but we can actually find the hypotenuse by doing 2,000 squared plus s squared is equal to h squared, square root both sides. And so I can use that for my hypotenuse in my cosine squared theta. And then I don't have to worry about the angle anymore, theta, because I don't have anything to plug in it. So we'll keep plugging in. So in place of cosine squared theta, I am going to have my adjacent side of my angle over my hypotenuse, which is that thing we just found. I'm not going to simplify anything just yet. Squared, because cosine squared theta, times t, which I know is 10, all over 200. So I have this ugly thing, but if you notice, I no longer have any variables, and so it's not as bad as it looks. So we should be able to simplify that carefully and plugging everything in. And so when we simplify this, the square root in the bottom of that fraction goes away, but you'll still square the top, so you'll have 4,000, and as you plug everything in, it works out pretty nicely, and it's not too ugly, and you can plug in your calculator, and you will get a beautiful value of 2 over 29. And your units in this, because you're talking about a theta, and you're asking for d theta, it's going to be radian instead of degrees. And then it talked about our time being measured in seconds, so seconds. Okay, so it's not the prettiest of functions, but it's not the ugliest of functions either. Okay, and that's a pretty complicated problem, but that might be something you would see on a free response for your AP test. All right, last example. These are my favorite, but again, it's very geometry. I mean, they're all geometry based, but I like looking at three-dimensional shapes. All right, so all edges of a cube are expanding at a constant rate of 6 centimeters per second. And we're asking how fast the surface area is changing when each edge is 2 centimeters and then 10 centimeters. So there's two parts to this question. We're going to do two different rates, okay? And so we are going to have to set up an equation for this, just like we did on our other ones. And it's talking about surface area. And so if you look in the back of your book, you do have surface area of it, but consider you're adding all faces of a cube, and the area of each square that makes up a face is s squared, and how many faces are there on a cube? There's 6. So the surface area is equal to 6s squared. All right, and so let's figure out what information we are given. We are given that the edges, in this case I call them s, they're all s, is changing at a rate of 6 centimeters per second. So ds over dt is equal to 6 centimeters per second. And then we're asked to find, and this looks ugly, but it's ds of a, okay, like that, because you're doing surface area, and you can't just call it s, and you can't just call it a, over dt, when s equals 2 and s equals 10, so two different instances. So let's take our function here that we have, and let's go ahead and do its derivative. So ds over d, or dsa over dt would be the derivative of surface area, equals to 12s ds over dt. Okay, and then we can plug in the information that we have. Okay, we know that ds over dt is equal to 6, so I'm going to have dsa over dt is equal to 12s times 6. Okay, now we need to do it at s equals 2 and at s equals 10. So I'm going to plug it in twice. So we'll do the change in surface area with respect to time is equal to, let's go ahead and multiply 12 times 6 so we don't have to do that every time. So we'll do 72 in this case times 2, and that is 144. And our units would be, it is a type of area. Okay, so we are going to have centimeters squared per second. And then we will do the same thing down here, but instead of plugging in 2, we'll plug in 10. So that we have 720 centimeters squared per second. Again, this is the last section of the chapter, so make sure that you're keeping with your homework because Friday you guys will have a test over